Hello students. In the first video lecture we discussed some of the algorithms and problems of operating system. In this video we are going to look into the remaining algorithms of operating system. The first topic I am going to take is the address mapping under paging. As we discussed in the class, paging is an important memory management technique. Under paging, all the processes are divided into logical partitions called pages, and the main memory is also divided into logical partitions called frames, and the size of the page and frame is chosen to be of a same size. Now in this arrangement we have got two possible scenarios where problems can be expected. One condition is that we are given the size of the main memory, size of the logical memory, and the size of the frame also. Now we have to compute the size of the logical address needed for the given logical memory, and within the logical address how many bits are to be used for representing the page number and how many bits are to be used for indicating the offset. So we have to compute that part. The second kind of problem is that given a logical address, how to map it into a physical address with the help of a page table. So these two are two possible problems you should expect. To understand the first problem, I am going to take this sample problem. So here we are given that the size of the logical memory is 4 MB and physical memory size is 1 MB and size of each page is 4 KB. Because the page size and frame size is same, we can assume that the frame is also of 4 MB size. Now the first thing we have to calculate is how many bits are needed to represent the memory. So what is the size of the memory address? That calculation has to be done with respect to the 4 MB, because address is always with respect to logical memory, not to the main memory or physical memory. So for 4 MB, how many bits are needed? For that we have to convert 4 MB into number of bytes, because for each byte of memory we have to provide a unique address. So we just have to first find out the number of bytes. For that we can just multiply 4 by 1024 so that we will know the number of kilobytes, and again if you multiply by 1024 you can get to know the number of bytes. The total number of bytes present in 4 MB is 41,94,304. Now we have to now decide how many bits are minimum needed for providing a unique address to each of these bytes. As for calculation, we need minimum of 22 bits, because 2 power 22 is equivalent to the value of 41,94,304. So we have the answer for the first question, which is 22 bits, which is nothing but unique address for each byte, starting from 22 zeros as this first address and all 22 ones as a last address. So because of this requirement we fix 22 as the address size. Now the second information to be calculated is number of frames. So number of frames out of the main memory, because frames are part of the main memory, so this question has to be treated as related to the main memory size. So the size of the main memory is 1 MB. So the simple calculation we have to do is that within 1 MB how many 4 kilobytes are there. So we just have to divide 1 MB by 4 KB. For that we can do this calculation, 1024 divided by 4, because 1 MB is equivalent to 1024 KB. So just divide 1024 KB by 4, you get 256 as the answer. That means there are 256 frames available in the main memory of 1 MB. The second is a similar problem, except that it is asked with respect to the logical memory. So within 4 MB how many pages are present? Again you do the calculation, but now we have got 4 MB, so we have to multiply 4 into 1024 so that we know how many kilobytes are in the 4 MB of memory, and then you divide it by 4. So 1024 pages are existing in the logical memory. Now the next calculation is needed about offset and the page number. So let us take the page number first. So how many bits are needed to represent the page number? We already know that each page is the size of the page is 4 KB And we also have calculated that there are 1024 pages totally present in the memory, logical memory. So we have to calculate how many bits are needed to represent 1024 pages with unique addresses. Again we have to use a 2 power logic. So 2 power 10 is equivalent to 1024. As a result, the number of bits needed for representing the page number is 10 bits. So out of 22 bits, we are going to reserve 10 bits for page number, and apparently the remaining 12 bits are to be used for the offset. So we have calculated everything given which is asked in the problem. So logical memory address will be 22 bits. Number of frames in the main memory will be 256. Number of pages in the logical memory is 1024, and 22 bits will be split into two parts, 12 plus 10. That is 10 plus 12. So the first 10 bits will be telling us what is the page number, and using which we can find the frame number with the help of the page table. After that, we will combine the frame number with the 12 bits of offset to produce a physical address. The second problem you can expect in this topic is, given a logical address, you should be able to map it to or translate to a physical address. For that you are given all the needed information. So let us first try to interpret the details. So what we understand from the sample is that there is a logical memory consisting of 4 pages. So the 4 pages are having each 4 bytes, because there are 4 alphabets. We can treat that each page consists of 4 bytes. The page index starts from 0 and it goes up to 3. So 0 to 3, there are 4 pages, and we can also easily say that the starting address of each page, page 0 starts from address 0, and page 2 starts from address 4. Like that we know the base address of each page. This is needed in the calculation we are going to do, and we are given a page table. So the page table has got some sample frame numbers. So each page is loaded into a certain frame number, and now we can see the physical address. So the physical address is comprising of frames starting from 0 to frame 7. Now the problem we are asked is 13. So how to convert 13 into a physical address? We can just follow these steps. First step is, you find out under which page number 13 could be present. Just divide 13 by 4, because the size of a single page is 4. Just divide 13 by 4, you get 3 as the answer. That means page 3. So page 3 is having the logical address of 13. Step 1. The second step is that locate the frame number of page 3 with the help of the page table. So you just go to the page table and use 3 as an index, and you find the frame number as 2. So you know the frame number now, and you should now calculate the base address of second frame. Without even looking at the picture, you can say that it must be 8, because a size of a frame is 4. So you just divide 4 by 2, 8 is the answer. So the starting address of the second frame is 8. Now what is finally needed is that you have to add the offset with 8 to get the exact physical address, because frame number or the base address of frame is only the starting address, but what you need is a exact address. For that you just add the offset. You can even use the formula for calculating the offset. Take this logical address and divide its base address, that is the 12. You get some value. You just add that with the base address of the frame which you found earlier. So add 1 with 8. What you get as a result is nothing but the physical address. So following these steps, you can convert any logical address into any physical address. Another example is logical address 3. As we just did in the previous slide, you find the page number that contains 3. Dividing 3 by 4, you get to know that it must be in page number 0, and you also know the offset, because 3 minus 0. So logical address minus its base address, you find out the offset. Next step is, you go to the page table and you find the its frame. As for the page table, page 0 is in frame 5. So you know the frame 5. Now you have to calculate the base address of the frame, and as we did in the previous example, just multiply by 4. So you get to know the frame number, starting address or the base address of the frame 5, 20, and you add the offset. Offset you already calculated. So 20 plus 3, which is 23, is the physical address equivalent to the logical address 3. Let us verify it. So 3 contains a D, and if you go to 23, you also find a D here. That means what you found is the correct answer. In the same way, you can also do a calculation for logical address 4. So this is the second problem that can be expected in the topic, converting a logical address into physical address with the help of the page table. The next topic is also part of the paging, but it is about page replacement algorithms. So we discussed in the class the context of page replacement algorithms, when they will be required. So whenever a page needs to be loaded into the memory frame due to a page fault, as long as there are available frames or free frames, we don't need to replace anything. We will just place the frame page into a available frame, and its execution will resume. But if there are no frames available, then a replacement becomes inevitable. And how to replace and which page to replace is an important question, because replacing a wrong page will result in too many page faults. So we have a number of algorithms to make that selection. We will be asked to apply any of these algorithms into a given problem to find out the number of page faults it could produce out of the given frames. That is the essence of this topic. So we take this problem for applying the various algorithms. So we are given that there are 3 frames in the main memory. So this information is essential, without which we can't do the calculation. So number of frames we have to assume has to be provided in the question. So in the given sample there are 3 frames. And the second information needed for this problem is the requirements of the pages. So in which pages will be referenced by the CPU, we have to make an assumption of a problem. Here the assumption is that first page 7 will be needed, followed by 0, 1, 2, 0, like that. And you can also notice that the same page will be referenced again and again. Now given this problem, we will have to apply the different algorithms to compute the page faults. First, let us take the simple algorithm of FIFO. So FIFO algorithm, as we know very well, it always replaces the oldest page, or the page which entered earlier will be replaced for bringing a new page. So it can be applied like this. Because there are 3 frames, we have got 3 boxes. Each box represents 1 frame. So the first page that will be referenced is 7, and because 7 is not there in the memory initially, we have to bring 7 from disk into the main memory, which we can treat as a page fault. So the first page fault has just happened. We have to make a count of the page faults. So we have to add 1 with the number of page faults. Next 0 is referenced, and that is also has resulted in a page fault, and then 1. So but till now we haven't done any replacement, because there were free frames. But hereafter, if any new page is referenced, we have to do a replacement applying the logic of the FIFO. Next, page 2 has been referenced, but because the frames are already full, we have to replace something. That replacement has happened with respect to 7, because out of the 3 pages currently present in the memory, 7 is the oldest one. It came before the remaining 2 pages, so it is chosen as a victim page, and 2 has been brought into that space. And next we are asked to get a 0 by the CPU, but since 0 is already existing in the main memory, no need to do anything, that is no page fault and no replacement. So we just proceed to the next request. The next request is also resulting in a page fault, because it is also not in the main memory and there is no frame available in the memory. So we have to apply the FIFO again. You find the second oldest page, and as we can see clearly, 0 is the second oldest page which gets replaced. So this is the way the page replacement will happen as per FIFO algorithm. So every page fall has to be counted, and finally we have to mention the total number of page falls generated out of this algorithm. If you continue to refer and replace pages, it would have resulted in 15 page falls. So as per the FIFO algorithm, for the given problem, we got 15 page falls. Now let us try to see whether the next algorithm either produces less number of page falls or more number of page falls than the FIFO algorithm. The next algorithm is certainly we can assume that it will produce less page falls, not just with respect to in comparison to FIFO, but even if you compare with any other algorithm, it will always be the lowest one, because its logic is always trying to replace a page which is not going to be needed in the future. That's called optimal page replacement algorithm. So the idea of the optimal algorithm, as I just mentioned, you look at the future requirements of the pages and find a page which is either never required in future or at least not required in the near future. That page gets replaced, and you will be having a situation like this. So for the first 3 pages, we can assume that they have been brought in without any replacement, but when it comes to 2, now we have to apply optimal. But optimal can be implemented only if you have a view of the future requirements, unlike FIFO. We can't look at the past. FIFO is based on past oldest page, but optimal is about the future. So you have to look at all the future requirements and find out of the 3 pages which are currently occupying the memory, which one will be not needed or not needed in the near future. So 7 is going to be needed somewhere towards the end, 0 is immediately needed, and 1 is needed in between. And seeing the 3 requirements, we can clearly see replacement of 7 is the best choice, because we can avoid a page fall for a longer duration by replacing 7. So the optimal replacement will remove 7 and put 2 in that place. So this is the idea of the optimal replacement. So we have to scan the future requirements and replace a page which will be not producing causing a page fall for a longest time, and accordingly we will be getting 9 page falls, which is much lower than the FIFO algorithm. But practically we know that optimal replacement is not always possible, because we won't be knowing the future requirements of the page references. The CPU will only tell what is the page that is currently needed. It won't say that I will be needing these pages in future. So we can use only the optimal algorithm only as a reference technique to compare and analyze other algorithms. We can use this algorithm. The next algorithm is called the LRU algorithm. So the LRU algorithm is based on the idea of least recently used page. So whenever you are required to replace a page, again you look at the past. Just like FIFO, here also you will be looking back at the past, but instead of looking at the oldest page, we look at the page which was not referenced in the near past. So out of the given choices, the page that was least recently referenced will be removed from the memory. So for example, if you look at this case, 701 followed by 2, you have to replace 7 because it was the one that was referenced very too early. So out of 701, 7 was the page that was referenced before the other pages. So it is the least recently referred page and it gets replaced. So in this way you have to proceed with the replacement of the pages, and that will result in 12 page falls for the given sample, which is better than FIFO but not better than the optimal. And the next algorithm is called second chance algorithm. Second chance algorithm is actually is an improvement of FIFO algorithm or a modification of FIFO algorithm. In FIFO algorithm, we blindly replace the oldest page, which is not always appropriate, because sometimes the old page may be a frequently needed page. So replacing that may cause a subsequent page faults. So we try to enhance it by adding a reference bit with each pages. Whenever a page is referenced in a particular time quantum, it will be getting 1 as a reference bit. So it will be changed from 0 to 1, and like that every page will be having its own reference bit, which is either 0 or 1. So 1 indicates that that page was referenced recently, 0 indicates that page was not referenced in the recent time. Now when you want to replace a page, you just have to go to the oldest page or the first page in the queue and see whether its reference bit is 0 or 1. If it is 0, you just straight away remove that page and bring the new page into that space. If not, you try to give a second chance to the algorithm by setting or resetting the 1 into 0, and you proceed to the next page. The next page may or may not have 0, and if that is not if that is also not 0, then you also reset it to 0 and give a second chance. So like that you have changed all the reference bits to 1 without replacing any of them, and finally you encounter the page which has its reference bit as 0. That means it is the page to be replaced. So it is a next victim, and this page will be replaced. This is the idea of the second chance algorithm. But in case if you have got all the reference bits as 1, then the algorithm will reset everything to 0, and finally it will return to the first page again and will replace it. It degenerates into normal FIFO if all the reference bits are equal to 1. This first page will be replaced just like normal FIFO. This is the algorithm called the second chance algorithm. So with that we just have discussed the page replacement algorithms. Now we are stepping into the next category of algorithm called disk scheduling algorithms. So here the requirement is that we will be given a number of tracks or the number of requests of various tracks, and we have to apply the different algorithms so that we try to minimize the seek time. Seek time means that the time needed to go from one track to another track. So how to reduce the total seek time is the objective of this topic. We have a list of algorithms available for the category. So a sample problem will be like this. So consider an example of a disk which has the head as the initial position. Remember, for this problem the initial position of the head is an important value without which we can't do the calculation. So we need to know at the beginning of the problem where the disk is located. In this example they have given that it is 53, and next we are given that these are the various tracks to be accessed either for read or write. So we have to go to 98 and then we have to go to 183. Similarly there are different tracks to be accessed. Let us first apply the FCFS algorithm. FCFS algorithm will not try to improve the result in any way. It will just go by the actual order, which means it will go from 53 to 98, and we have to calculate the tracks which are being crossed or traversed while going from 53 to 98. So to go from the source to destination, how many tracks were crossed, which is nothing but subtracting 53 from 98. You just find the difference between the two numbers, which is 45 in this case. Similarly, after reaching 98, it will then go to 183 because it's FCFS. It will just go in order. So again we have to compute the difference 85. Like that, if you just move from one request to another request, finally you will be getting 640 as the total number of tracks, which is nothing but the total seek time we computed for the given sample data. So we have to apply the different next algorithm for the same problem, and this is the graph that was produced for the FCFS. So we can see that from 53 it went to 98 and then it went to 183. Like that it reached the last track. Next algorithm is actually a better algorithm because it tries to reduce the seek time by always going to the nearest track. So as for the given request, it will go to the nearest track from the current track rather than going to the next track in order. It will go to the nearest one. So as for this, it will go from 53 to 65, producing a difference of 12, and then from 68 it will go to the next nearest one, which is 67. In the same way it will traverse. It won't go to the tracks in order, but it will go to the nearest ones, and ultimately it will produce significantly lesser value comparing to FIFO. In this case it is 231. Remember that we got 640 in the FIFO algorithm, so this must be very low. This improvement happened because of this logic. And once again the graph is indicating the same order. The next algorithm is called scan scheduling. So there is a logic behind the scan scheduling. Here what happens is that the head will move from one direction towards the other extreme, and then it will start going up. This is the simple idea of scan algorithm. So as we can see in the graph, from 53, which is the initial head position, it goes to 0, which is the lowest track, and while going to 0 it takes all the requests. Whatever comes in the way, it serves them. So 37, 14 are served as it is going towards 0, and after reaching 0 it tries to go to the top, and again the requests are taken. So 0 to 65, 67, 98, 122, 124 and 183. Remember, it doesn't go to 199 as it was going to 0. It doesn't go to the last track in the other direction. It ends with the last request. And as we did in the previous two algorithms, we have to compute the difference. So what is the difference between 53 to 37, 37 to 14 and 14 to 0, and likewise you have to calculate the result. The C-scan algorithm slightly differs from the scan algorithm. It goes to the last track in the other direction. Instead of going to 0, it goes to 199 and it takes request. But after reaching 199, it straight away comes to 0. Remember, we should not be adding this difference into the result. So while computing the result, we should not take the difference of 199 and 0 and add it to the result, because it's not taking any request while returning. It is as if straightly jumping into the 0th track, and from the 0th track it goes up, and while going up it takes the request. So the essence of C-scan algorithm is that it only takes request in one direction, not in both direction like the scan scheduling algorithm. And we have two algorithms which are slightly modifying the behavior of the scan and C-scan algorithm. In the scan algorithm, we noticed that it goes to the 0th track even though the last request is only at 14. This unnecessary traversal can be avoided, which results in an algorithm called the look algorithm. So the look algorithm follows the same logic of scan, except it doesn't go to the 0th track. In the same way, we can also avoid the traversal in the C-scan algorithm, avoiding the going to the 199. If you end with 183, then it's called the C-look algorithm. So these are the various CPU scheduling, disk scheduling algorithms. So a typical problem is like you will be given the initial head track position, total number of tracks in the disk, and the different requests. So you will have to compute the total seek time as per the algorithm that are asked in the question. So with this we are completing the second part of the video. So we have covered almost all the topics which are having the potential of problem being asked. So you have to be prepared on these algorithms and problems. Thank you.